Welcome to the TI-84 training for Math 9, and this is activity number 6. So locate activity number 6 on the TI-84 training for Math 9 website so that you can open the document and follow along. As follow-up to this activity, you will be posting screenshots. Having done these steps, you'll post screenshots to this document, and then you'll store this document under completed activities so that it can be reviewed later. Okay, so let's get started. The outcomes of this activity are graphing a complete function, generating a table of instantaneous velocities and differences, using a table to look at patterns basically, and it's much like a spreadsheet, the functionality of the table on the TI-84. Using the dy dx calculation tool to find the instantaneous velocity at a point, doing a quadratic regression, and then using the inderive feature to graph a function, but also using inderive to fill out our table from above. So to get started, let's look at an applied problem. It said an experimental rocket lifts off vertically. Its altitude in feet, t seconds into flight, is given by s of t equals negative t cubed plus 96t squared plus 5. And let's look on the domain t equals 0 to 100 seconds into its flight. So s of t is the height in feet, and t is the time in seconds. So it says use the table feature to set the window to obtain a complete graph, and embed a screenshot of both your window and your graph. So let's first input the function into the calculator, negative x cubed or negative t cubed, and of course we have to use x in place of t and y in place of s of t for our function, plus 96t or x squared plus 5. So when we first look at a window, it's set at whatever we last set it at, or at the standard setting as you see here. So remember, our x values stood for time, and we're told from 0 to 100 will be the times. Now our y values are the heights of this rocket, and we can try to do this by trial and error, but the table gives us a good way of approaching this. So our minimum height should be 0, at least when the rocket plunges back to Earth again, if it does, and we know what goes up usually comes down, right? And then our maximum height we don't yet know. So we can go to our table feature, and I can look at some various values of time, and these are residuals from perhaps another graph another time, but I can use them or delete them, and you'll see that I'm deleting them there because I'm going to actually plug in 11 would have been fine. But so we know that maybe at 10 seconds into flight the rocket is at 8,600 feet up. 50 seconds into flight, it's at 115,000 feet, and 60 seconds maybe, I can just keep trial and error, 129,605 feet up. 70 seconds later, ooh, it's only 127,000, only 127,000 feet up. It started to drop. So somewhere in here it reached its maximum height, and now it's starting to fall back to Earth. And so if we set our window at around 130,000 feet, maybe a little higher, as our y maximum, that should give us a complete graph. I'm going to go ahead and go to 150,000. And now we're ready to press graph. So you'll want to use the TI Connect software and take a screenshot of this graph along with a screenshot of the previous window, and you'll cut and paste those screenshots right into this Word document as part of your completed assignment for activity number 6. And this is also how you could informally assess your students as to whether or not they're understanding, because by activity 6 we have obtained complete graphs of functions before, and so you could just ask for them to do a screenshot and quickly glance at it to make sure that that or the window are appropriate for this particular function. Alright, so our second question is, what is the initial velocity of the rocket at time t equals 0? And it says use dy dx. Okay, dy dx is located under the calc menu. After we have a complete graph, this is its height over time, and so the slope of any tangent gives us the velocity from earlier activities. So we can calculate numerically the instantaneous velocity using the dy dx key, and it's located under the calc menu. So to access that, press second, trace, or calc. We're just going to select or press number 6, and then we're going to put in the time 0. So our time is at 0, and when we hit enter, the calculator is going to tell us that the height at time 0 was at 5, indicating that the rocket was up on the launch pad 5 feet above the ground, and that our velocity, because it's a numeric calculator, we have a little bit of error here because it calculates the derivative or the instantaneous velocity numerically. But in scientific notation, that's very close to 0, and you might as well round that to 0. So the initial velocity of our rocket at time t equals 0 is in fact 0 feet per second. So how can we use the table feature rather than having to use the calculator repetitively or redundantly to do every single value that you find in the table? Well, just to do one more example, let's go back to second calc or second trace or calc, and let's calculate the velocity of the rocket at time t equals 10, just to get our table started. So at time 0 we had 0 was our velocity. At time 10, so second calc, number 6, it's going to prompt me for an x value, put x equals 10 in, and hit enter. Alright, so unlike the previous example, the dy dx now is 1,620, so we would put in that the velocity is 1,620. Our units are in feet per second. Our altitude there is 8,605 feet. Now, first differences and second differences won't mean anything until we've filled these columns out. But there is a way that we can program our table, or use the table to fill out this entire table in one quick step. So that's what and so our altitude was 5 at time 0, and our velocity was 0 at time 0. Your first differences are the differences between these two values, subtracted in this order. So we would take 1,620 minus 0, and that first difference should show as 1,620. So we'll get to that momentarily. So the first thing we want to do is, in order to use our table, is we have under y1 is our function of x. Under y2 we want the derivatives, or s prime of t, at those various values of time. So we can use the inderiv or inderive function right in the table. And if I press math and go down to just number 8, it's going to put inderive right in there. So under y2 I went math and then pressed number 8. It puts inderive in there. We have to put our function in first as part of our syntax. Well, the quick way to do that is to press the vars key, go to yvars, function's already highlighted, hit enter, and y1, just hit enter, and it pastes what's under y1 right into the inderiv or inderive function. Now hit the comma key. Now we have to tell it what variable, and our variable is x. And then because we want it to do it at each value of x from our table, we put in x again. If we wanted just a single value, like at 10 seconds, we could put in 10, and it would generate 1,620. But because we wanted to do each value in the table, we'll put in x here. And just checking this, let's check our table real quick and go second table. So at 10, I have 8,605, and indeed I have 1,620. Now, if I go to 20, it'll automatically fill in my altitude and my velocity at 20. And the same thing for 30 and for 40. 60 and 70. Now what we could also do is we could use an auto feature, and if I hit second table set, we start our table at 0 and we increment our table by tens every time, and we put this on auto instead of at ask. This will keep generating the table not only from 0 to 80 as we're asked in on the activity, but from 0 all the way up as far as I'd like to go, and all I have to do is continue to go down. But at some point we're going to hit the ground with the rocket, and that some point is going to happen between 90 and 100 seconds, so there's no reason to go any further in the table. But this is another way I could use the auto feature to generate the tables, and there's no reason to go back in time, so there's our table generated from 0 up to 100 seconds, even though we were only asked to fill out the table from 0 to 80, so we'll use that portion of our table here pretty soon. Notice this column is our instantaneous velocity. So what happened is the rocket reached 130,000 or so feet, but it's slowing down. Its velocity at 50 seconds was 2,100 feet a second. Its velocity at 60 seconds is 720 feet a second. That's a pretty huge reduction. And then suddenly the velocity has changed to negative, indicating not that its speed has changed, but its direction. So now it's starting to head back to Earth, and you could see that because now it's not as high as it was at time t equals 60. So somewhere in here it changed direction, and we saw that from its graph. Alright, now we would like to have first differences. So the first differences are the differences between two subsequent red values in the table here. So the first difference would be right here would be 1,620 minus 0 would give me 1,620. Our first difference here would be 2,640 minus 1,620. So to make the table do this automatically, we can go back to y equals. And we want our next column to be the differences in our y2s. In other words, subtracting our y2s. So here's a way to do that. To get a specific value out of your table, we go to vars, yvars, enter y2. Now we put in parentheses, and we're going to put in x plus 10 because we always want to be at the next entry point in our table, minus, so then this is going to be a difference of the next value in the y2 column minus the one before it. And to subtract the one before it, we're going to go vars, yvars, function, y2 at x. So if we go back to our table now, what we'll see happens in the next column, which is going to show up in this dark color here. In this next column, I do get the 1620 minus that is 1620. 2,640 minus 1620 is 1020. 3,060 minus 2,640 is 420. And if we keep subtracting in the same order, this 2,880 minus 3,060 is minus 180. So you'll see now that we went to negatives here. We would like our next second differences to be the differences of these values. And so that's really easy to accomplish. We go back to y equals, and following sort of a similar pattern, we want the differences this time to be the differences in our y3s. Vars, y vars, function. y3 is under number 3, so I can just punch number 3 there and it puts it in. X plus 10, which is the next entry point in the table, minus our y3 at x. And so to do that, we hit vars, y vars, function, y3 is 3 of x. And that has to be in parentheses. And going back to our table one last time, you'll see that these are our second differences. They'll be under the pink column. And it's taken just a little bit of time for the calculator to generate the first few. So your table from 0 to 80 is complete, and this screenshot is what you'll want to present. So you can present a screenshot, or you can manually fill these values in, but it's really nice to be able to use the calculator to automatically generate altitudes, velocities, first differences, and they are subtracted, the next one minus the previous one. And then the second difference is done the same way. When the second differences are constant, that tells us that the velocity function that we're looking for, that these values, because their second differences are constant, must be quadratic, or a degree 2 polynomial function. Now, in terms of learning to do the derivative algebraically, this is our displacement function is a cubic function already. So clearly by the power rule, and really the power and sum rules for taking the derivative of this function, we have an idea that the derivative function s prime of t, which is the velocity function, should be quadratic. But this is a data-driven approach, so we can go and look at our table, as you see here to the right, and because our second differences in the table are all constant, we know that we are looking at a quadratic. So now we can actually go into our table one more time, and we're going to actually clear the table contents. We're going to clear our table because what we really want is we want only our velocities and our times. So we're going to use this column and we're going to use this column in an analysis or in a quadratic regression shortly. So to embed, you can embed either copy this table or, as it said there, use a delete key and just generate the table of values for just this portion of the table that you want, and then embed a screenshot. This is what I'm actually looking for right here, but on your own calculator. Alright, so notice because the second differences are constant, that we're looking at a quadratic function. And our calculator has a great feature called quadratic regression that we can use to come up with, to obtain this velocity function that we're after, strictly from these data points that you see here. So we're going to need these data points and the data points that you see here, and we're going to put these into our stat edit. So we're going to go to stat, and we're going to hit edit. And what we want is we want to look for the lists L1 and L2. Those are the ones we're going to use right now. If there's anything in list L1, we hit clear. We highlight and make sure that we're highlighting the list name. We hit clear once and we down arrow, and that data goes away. So under L1 is we want our velocity, Under L1 we want our times 0 through 80, so we'll just go and input each of those times 0 through 80. And technically we don't even, to tell you the truth, we don't actually have to have all of these values, but the more the merrier. And the regression feature, if the data was not perfect, using these values 0 to 90 or 0 to 80 would be great. So we'll go 0 to 80 right now. Yeah, 0 to 90 is fine. And then we need our velocities. So if you remember, right, our velocity at time 0 is 0. And then our next velocity is 1,620. And our next velocity is 2,640. And I wish there was a nice way to cut and paste on the TI-84, but and there might be a trick to it. 3,060, 2,880. So it looks like the velocity was increasing, and suddenly the velocity is decreasing, and that probably means the rocket booster has long burned out the rocket engine where it was accelerating and increasing in its speed, and now it's still moving upward, but it's starting to be slowed by the effects of gravity. At 50 seconds, our velocity is 2,100. And then 720. And I'm just getting this right off of the same table that we had a moment ago. And then we're at negative 1,260. And at 80, we're at negative 3,840. And I think that's enough. So I'm going to hit delete of that one value. So we have our L1 list, which is our times in seconds. Then we have our L2 list, which were our velocities in feet per second. So the negative velocity means it's on its way downward and it's moving pretty fast. But that doesn't mean it's like a negative speed, negative velocity. Alright, from here we press the stat key, we go to calc, and we go to number 5, which is quadratic regression, and I can just press the number 5. Now if you have your stat wizards turned on, this is what it will look like. If not, we just hit enter one more time, because the default is in fact the list L1, L2 where we store the data. So if it looks like this, go down to calculate. If not, just hit enter. And the quadratic regression will give us the following quadratic function: negative 3x squared plus 192x plus 0. And then the next line under that shows that our correlation coefficient is essentially perfect, that this data is exactly quadratic. Well, we kind of notice that from the second differences of our table. But in particular, it gives us the second derivative function. And so we can write down the function v of t equals negative 3t squared. Okay, now x is in the place of t, but we're going to go ahead and be negative, or positive, negative 3t squared plus 192t. And I'm going to highlight this or put this in a different color, so let's go ahead and put this in a green color and bold it, because it's one of our answers. So we obtained from this quadratic regression, from data, we obtained this velocity function. Well, at this point in the semester, no doubt, we're learning to find the derivative. And so if I use the power rule, I would indeed get, the 3 would roll down, and I would get negative 3t, and then subtract 1 from 3 gives me the negative 3t squared. And then rolling this down, 2 times 196 is 192t, and the derivative of the constant is 0. So we can verify that the quadratic regression gives us exactly the same thing as the power rule gives us. But I wouldn't tell the students that if they hadn't had the power rule yet. That's just the power of using the calculator. And again, you'll want to post a screenshot of this quadratic regression under number 6 here to see how it works, so that for future reference. Okay, now what we want to do is we're going to return to y equals on the calculator, and let's clear out everything that you see here under y2, y3, y4, and instead of the original function, what we want to graph here is our velocity function, negative 3t squared plus 192t. Again, using x in its place. Now, our domain is still on the same domain, 0 to 90 or 0 to 100, but our range, our velocities, if you remember back to our table, only went up to about maybe 4,000 feet a second and negative 4,000 feet a second. So under our window, let's have our velocities are now anywhere from maybe negative 4,000 to about 4,000 feet per second. So that's a realistic domain, and again, you can just actually post this or embed a screenshot of this if you wanted, and of your window that you set on a realistic domain in order to satisfy number 7 for the activity. And then finally, one of the last things we want to do is we want to verify this graphically. And so what we're going to do is we're going to go ahead and go to y equals. And to turn off a function, all we have to do is highlight the equals and hit enter. And that'll actually turn it off from graphing. So if I hit graph now, you're going to see nothing show up. That turned it off. And what we're going to do is we're going to hit y2. And immediately when I arrow down to y2 and I start inputting something, and we're going to use the inderiv of what we had before. So we're going to go to math. Number 8, our function, our original function, if you recall, is negative x cubed plus 96x squared plus 5. We can no longer just use y1 because we have something different under y1, and we're just storing it there. Comma, we need the x, and then x. So now when we press graph, we have our domain already established. We're going to graph a red curve because it's turned on, but the blue one is not turned on. So when we hit graph, now it takes a little bit longer because it's having to calculate at various values of x the derivative of the function that we put into it, and then plotting all those points and finally connecting those points. So a little slower because it's computationally having to do a computational step. So does that look like the embedded screenshot from number 7? And we can just verify that. We can turn both of these on. Press on to stop the graphing process. Highlight equals and press enter. And now when I press graph this time, it's going to superimpose the blue one and the red one. So it's showing that the inderiv, that our quadratic regression and our inderiv were two ways of arriving at the same velocity function, which is a parabola. It's a downward turning parabola. And then of course we could in fact use y1 or y2. And let's hit trace. So at 50 seconds our velocity is 2100 feet a second. Where is our maximum velocity? Let's just trace back a little bit. Our maximum velocity happens where? 3069, 3071.9, and then it drops. So just by trace, this isn't exact, it looks like our maximum velocity is right around 3072 feet a second and happens at almost 32 seconds in, 31.8 seconds into flight. So what real world analysis what meaning can you give this? What happened at 31.8 seconds? And of course this is when the rocket's burnt out. The rocket boosters actually ended. It stopped accelerating, and at this moment it starts losing velocity. So it's only, roughly a half a second later or so, a little bit more, and it's lost barely any. But it's starting to lose velocity now as we continue on in time, and that's due to gravity, because it's no longer being accelerated. Now gravity starts taking hold of it, and the velocity continues. We could continue to decrease in both its speed and its velocity until it gets to a velocity that's near zero, and that happens between 64.6 seconds and 64.4 seconds, 63.6 to 64.4, so roughly halfway in between there. And we can use tools like our zero to find out when was the velocity exactly zero. So I need a left bound, it says. I have to make sure that my velocity is positive there. I need a right bound, make sure my velocity is negative there. Hit enter, and it looks like at exactly 64 seconds into flight, my velocity was zero. So what's velocity zero mean? Well, velocity zero means that it's reached its maximum altitude at this point as well. So if we wanted, as part of the activity for your students, you could include some other questions you ask in analyzing this graph, and those are part of some earlier activities that we did. But coming up with this velocity function and then using it to answer a few questions is an excellent way to foster understanding. So this concludes activity number 6. In order to complete the activity, please put, basically include screenshots or answers to each part of the 8 questions that are on activity number 6, and then drop the Word document with the heading into the folder at the top of the website.